Acid and bases might be all I remember. So chapter 13, acids and bases. So last time we talked about pH of strong acids and bases. And again, remember that if you have a strong acid or base and you're actually sort of given the formula of it, you can basically calculate the pH of it because of the understanding that it is a strong electrolyte. So it will 100% break apart. So once again, if you have something like hydrochloric acid, it is going to completely dissociate into its ions. And because of that, you basically, for the pH, would just need to know the H plus concentration. And as long as you kind of know the molarity of this guy, you could do a little stoichiometry there and figure out the molarity of the H plus. And that can then go into your pH equation, obviously. You can do that also for a strong base. If you have something like potassium hydroxide, which is a strong base, it will also 100% dissociate into ions. In this case, though, actually it's the hydroxide that you would be interested in terms of the molarity. That would let you get not the pH, but that would also allow you to calculate the pOH. And once you have the pOH, you can get yourself there to the pH in this particular case. Remember, in terms of strong bases, that's like your lithium, sodium, potassium, calcium, strontium, barium with hydroxide. So kind of group 1 and 2 that has hydroxide in it. And again, we have that sort of list of strong acids, HCl, HNO3, HClO4, H2SO4, HBr, and HI. So again, that's kind of the 6-pack of strong acids happening there. Now, this is different again than weak acids. So again, weak acids are weak electrolytes, which means they will set up an equilibrium. So you will get an equilibrium type of reaction that occurs with it. And here we would still be interested really in the H plus concentration, but because it's an equilibrium, we do need to take an ice table approach to these calculations. The end result is we're looking for what the H plus would be at equilibrium, which in a lot of cases will be the X that you get when you actually solve for X from the ice table. And once you have that, you then can go into your pH equation there. Guess what the H plus would be good as well. Remember that we could solve these just like we solve any other equilibrium type of problem because it is just an equilibrium problem, pretty much. So we could perfect square it, we could quadratic it, we could try the assumption if it works. Again, a reminder that you do need to check your assumptions. So we had a couple, I think last time that technically didn't work, so you had to go back again and solve that some other way. Any questions on any of that stuff there? Okay, then we talked about acids, so why not bases? Seems like fun. So we can also apply the same approach to weak bases. And once again, much like our weak acids, weak bases will not 100% dissociate. And they will then be really weak electrolytes that will set up this equilibrium. NH3 is your popular weak base. And unlike, for example, weak acids or acids in general, when we show it sort of just breaking apart in water, and we don't necessarily include the water in the equation, I would recommend them for bases that you actually do include the water because it just helps you maybe visually see what is going on here and where the hydroxide actually comes from. With the acids, because it breaks apart into H plus, you could kind of tell where the H plus comes from. But again, sometimes people struggle with like, where's the hydroxide come from? So if you're dealing with a base, I would probably include the water in the equation. And again, that will just hopefully think of it as a Bronsted-Lowry situation, and you'll be able to kind of figure out how we do get to this guy. Once again, this is an equilibrium, and we could write an equilibrium expression for this, and it is the same deal as all the other equilibrium expressions. It is our products over our reactants. Once again, here, water not included because it is a liquid, so just like normal. we would not include it. This is what's known as a KB. We can add that to our ever-growing list of K values: KC, KP, KW, KA, KB. We might be halfway through, I don't know, or so. So KB is obviously the ionization constant there for a weak base. And kind of the same idea as the Ka. As the Kb value increases, so does the strength of that weak base. So it's the same idea as we talked about with the weak acid. If you have a larger K value, that means you should have more products at equilibrium. And in this case, if you have more products at equilibrium, you will have more free OH minus floating around in your beaker, and thus it will be a stronger weak base than perhaps another weak base. Much like our weak acids, will we have Kb values for strong bases? We will not, for the same reason. A strong base is going to 100% break apart in solution, and it will not set up an equilibrium, but a weak base will. So again, this is a good way, just like with the Ka, if you see a Kb value given to you, then you probably should know it is a weak base. So again, you don't want to overlook that kind of information that's oftentimes given to you in problems and so forth, so you don't miss it. Once again, much like the acid part here, when we're talking about sort of the strength of a weak base, again, we could have a stronger weak base than another weak base, but all weak bases will be less strong than any strong base that we have. So something like sodium hydroxide will be a much stronger base than any of these sort of weak bases. Thank you. Any questions on that? So how do we solve these problems? The good news is we solve these problems the exact same way. It's an equilibrium. So once again, that automatically should scream that at you. Yes. So anything involving equilibrium is probably not usually the wrong move to lay up an ice table. We will do an ice table usually in these type of situations to figure out the pH, but there is a slight difference. At equilibrium, we actually will have the hydroxide concentration and not the H plus concentration. So when you're done here at equilibrium, you will have basically the concentration of hydroxide, which means you do need to probably go the POH route first and then into the pH. So again, that's also a very common mistake that sometimes people mistake it as maybe it's the H plus concentration and they go right into the pH, or think what they're calculating is the pH. This is also why it's extremely important to be able to write those reactions correctly, because you could hopefully visually see it's a hydroxide there, and that should remind you when you get to the calculation part that you actually are doing the POH rather than the H plus. I can't tell you how many tests or questions I've seen over the years where people will write this equation and they'll end up with H plus on the other side. Yeah, and they'll just do it thinking that's the pH they get. So again, super important to be able to write the equation correctly, part of the grade as well. But more importantly, it will help you with the calculation part, right? So that you hopefully understand what you're looking at. Any questions on that there? So as it says there, again, we're just going to solve it just like our weak acids. But again, we'll get that hydroxide concentration, and kind of the POH to the pH route is where we're going to go. Here's a table similar to one you got in your book of some weak bases. A lot of organic molecules that contain nitrogen are weak bases, and ammonia is a very common sort of weak base that we see. So why don't you give one a go here? We have an amine compound, which is a nitrogen-containing compound. The Kb there is 5.6 times 10 to the minus 4. What would be the pH of a 0.15 molar solution of C2H5NH2? Okay, so let's take a look, see how you're doing. So in this case, a couple of things, again, we want to think about when we see a problem like this. Again, the first thing that should jump out at you is we have a Kb value for this guy right here. So that should tell you, again, it's a weak base. And again, that should tell you ice table is probably the way to go for this. So we're going to start with our formula, which is C2H5NH2. And because it is a weak base, as I mentioned, I would include the water in that case. And if you're not sure what's going to happen in this case, once again, you should default back to the Bronsted-Lowry definition of a base, which is a proton acceptor. So basically what's going to happen in this case is it's going to send an H plus over there so that it can accept it. That pretty much means we have exactly the same thing, except I need to add one more H and also the plus that occurs there. The water, by giving up the H plus, is going to produce hydroxide, and hence why this is, again, a base in this case, because hydroxide was produced there on the product side. Any questions on that there? We'll do our ice table here. The only thing given to us there is we have 0.15 molar of this guy, 0 and 0. We could also write again our Kb value, our expression if we like, which would be the concentration of C2H5NH3 plus OH minus, and our original guy there, C2H5NH2. Once again, water not included as it is a liquid. Our change is going to be minus X as we only have reactants, so the forward direction here should predominate. And that means at equilibrium 0.15 minus X, X, and X. Any questions on the table here? We're going to then pretty much put that into our equilibrium expression. So that will give us basically that X squared over 0.15 minus X equals our Kb value that was given to us, 5.6 times 10 to the minus 4. You could assume that X is equal to 0 here, and you'll get X squared over 0.15 equals 5.6 times 10 to the minus 4. We will multiply to the other side, and then afterwards take a square root. And if we do that there, 0.15 times, right numbers, 5.6 to the minus 4, hit equals a little square rootage. And you'll end up with an X value of 0.009165. We do need to check it, so we'll divide that by 0.15 times it by 100, and then our disappointment will come into play when we see 6.1% perhaps happens in that situation, and it is not a good assumption in this case. So we do need to go back actually and solve it another way. So we'll go back and do our quadratic in this case. And again, we're going to basically multiply what's on the bottom to the other side. And that will get us X squared is equal to 0.15 times 5.6 to the minus 4. 8.4 times 10. I want scientific notation today. 1, 2, 3, 4, 5, I think, if I counted those zeros right. Minus, it's a 50-50 shot at that. 5.6 times 10 to the minus 4x. Obviously, when we multiply the other guy across. Going to bring everybody to the same side there. Going to get us x squared plus 5.6 times 10 to the minus 4x minus 8.4 times 10 to the minus 5 equals 0. That obviously is our A, B, and C happening here. Putting that into our quadratic, we got x is equal to negative 5.6 times 10 to the minus 4 plus or minus. We do everything inside the square root. That's going to be 5.6 to the minus 4 squared minus 4 times a, which is 1, times c, which is negative 8.4 to the minus 5. Going to get us inside the square root something like 0.003363, to which if you square root it, 0.01833 is what you should get, and divided by 2 times a, which is basically 2. That is going to get us 2x values here. Perhaps one is good, hopefully. Plus 0.01833. Difficulty with the calculator. All right. Like that's wrong. 5.6 to the minus 4 plus 0.01833 divided by 2. Third time's a charm here. Hang on. I took chemistry once. Let me see. Just once. All right, let's try that again. All right. There we go. Maybe I should take calculator. All right, 0.00889, we'll call it. R, obviously, if we do the subtracting one, we will get a negative value in this case. And that negative value, which is probably not going to do us much good, negative 0.009445. That's not going to do us much good because, again, we are looking for the hydroxide at equilibrium, which equals X, so it cannot be negative in this case. That would mean that that should be right there, our hydroxide concentration. And now if we go into our, it's still right here since it's on the same page. We go into remember our POH because our hydroxide concentration is equals 0.00889. POH here going to be minus the log of that. Gonna get us looks like a 2.05 as our POH. Once again, if for some reason you thought that was the pH, it really shouldn't make sense to you because this is a base, right? And clearly a pH of 2.05 is not basic. So our pH in this case would be 14 minus that. And that should move us to a basic pH of 1256, 11 something, 1195, it looks like maybe. 11.95, which definitely is basic in this case. Any questions on any of that there? Yeah. Say your question one more time. I'm sorry. Yeah.
So base is on the left-hand side as a reactant.
Okay.
Is it always the case that the H plus is going to be donated from the right to the left, like from the product side to the reactant side?
In this case, it will be donated by what's acting as the acid. And in this case, for most of your weak bases, what will be acting as the acid is the water. And that's where the base on the left-hand side is basically accepting the H plus from. And that's also when it does so, that is the conjugate partner really to the OH minus. So that's really how we produce the hydroxide in this case. And so that's where it kind of comes from. So that's why I said in terms of bases, especially weak bases, it's probably a really good idea to use the water in the equation and just know that the water will act as the acid pretty much in that case. And that will help you if you just think of it like the Bronsted-Lowry definition, it will give away its H plus. And again, that should hopefully help you understand that's where the OH minus will come from. Other questions? Okay. Now, let's talk about Ka and Kb. First off, you have a Ka value, which obviously is for a weak acid. We have a Kb value that is for a weak base. How do we know which one we should be using at any given time? That was a question, yes. Yeah, so the important thing here again, and it does come back to writing those equations correctly, which is if you see H plus on the product side or H3O plus on the product side, you definitely should be using a Ka value. If you write your equation and you see OH minus has been produced on the product side, It definitely should be a KB situation. So again, I can't tell you how many times people kind of mess that up because they really don't know how to write the equations. And it's really important to make sure that you use the right one. There will actually be problems that we will see very shortly where they will give you the wrong K value in the problem. They'll give you a Ka value when you need a Kb value, and they'll give you a Kb value when you need a Ka value. So again, it's really important to understand that. And the best way to know, am I using sort of the right one in this situation, is by what you see in the equation on the product side. So again, H plus H3O plus on the product side, roll with the Ka. Even if they don't give you the Ka, that is what you need if you're going to do a calculation. And if you got hydroxide on the product side, you need to roll with a Kb. By the way, if we add these together, that is our friend water, basically, as everything cancels out. That makes water, which we also know is a K value. That's our Kw. And we know that if we add these guys together, what do we do with those K values? We multiply them, yeah? So it gives us a really good relationship. If you take the Ka value times the Kb value, it will equal the Kw value. And that, by the way, is still that 1 times 10 to the minus 14 in most cases. Yes. You would if, like we talked about, if you did, but in this particular case, we didn't need to change anything. So we just added those two together. So you do multiply the K value. Clear, if you had to manipulate one of those reactions, then you have to manipulate the K value as well. Yeah. So this is a very good relationship. As I just mentioned, for those problems where they kind of give you the wrong value. So you can quickly kind of get to the correct value that you need by using that relationship. It is the same calculation regardless of what you're trying to calculate. You basically take Kw up on top, which is 1 times 10 to the minus 14, and divide it by the Ka value, and that will give you the Kb. Or you take 1 times 10 to the minus 14, divided by the Kb value, and that gives you the Ka, and so forth. So useful, definitely in some problems we're going to do in just a bit here. And a good way to kind of go between the two. But before we do that, let's talk a little bit about acid strength. And there's really two types of acids that we kind of come across. Ones that basically contain oxygen and ones that don't. And when we're dealing with acids that do not contain oxygen, we want to look at which one is a stronger acid. And you may think that what would be the sort of overwhelmingly thing that you should look at is electronegativity. And a lot of our acids that do not have oxygen is there in group 7, like our HF or HCl or HBr. Put an H there. Our HI. And you may think that, maybe it's electronegativity that's really the overwhelming thing that we want to look at. And it's actually not. So when we're dealing with this type of acid, we actually look at bond energy or bond enthalpy. And you might have talked about it when you did bonding last semester, breaking bonds, making bonds. I teach it. I don't know if anybody else teaches it, but there's a certain amount of energy required to break a bond. Now, why is that important? Well, what is the definition of an acid? It is the ability to release that into solution, right? So basically the ability to get rid of that H plus and let it go. That means that the stronger this bond is, the weaker the acid's going to be because not a lot of it's going to come off, right? The weaker that bond is between the hydrogen and whatever it's attached to, like the chlorine, the fluorine, whatever it may be, it's actually going to be a much stronger acid because it's not going to take as much energy to pop off the hydrogen for it to do its acid thing. And if we look at bond enthalpy or bond strength, we see actually in group 7, it increases as you go up group 7. And that means actually our weakest acid out of that group is actually F, which is our weak acid. These guys are stronger acids. It actually means out of that group, which one is actually the strongest acid? It's actually HI is the strongest acid, right? Even though we always think of like HCl, strong acid, it is a strong acid. But actually HI is stronger. It has a much weaker bond energy, which means you could break off that hydrogen a lot easier than you can, say, from HCl. And then it gets all super hard there for our HF, which makes our HF a weak acid in this particular case. So when you're dealing with something that is an acid and it does not have oxygen in it, you want to look at bond energy. Stronger the or higher the bond energy to break that bond, the weaker the acid, and the lower the bond energy, the stronger the acid. Now, when we deal with, and as you can see here, that's sort of the trend there as we go up and down there, strength increases. When we have acids that have oxygen, these are sometimes referred to as oxyacids because they have oxygen in them. And they usually will contain those polyatomic ions that everybody loves. You know, your eights, your ites, and bad memories, I understand. But they usually will also have an OH bond. And that OH bond is a polar bond because of the difference in electronegativity between the oxygen and the hydrogen. The oxygen being more electronegative than the hydrogen. So the oxygen is more negative and the hydrogen is more positive. So to begin with, we are starting with this bond where the hydrogen's going to try to come off. And it's already sort of weakened because they are sharing those electrons unequally, right? The electrons at this point are heading towards the oxygen, right? Which means the hydrogen just kind of hanging on there. So when we have a acid that contains oxygen, we look at two different things depending on the situation. We look at the electronegativity of the central atom, if necessary, or we look at the oxidation state of the central atom. And we'll talk about which one you should look at in which situation. So let's take a look at that. Now, if you have an oxyacid like these two right here, and the central atoms are from the same group and have the same oxidation number, what you want to look at then is electronegativity. So we are going to talk about oxidation numbers again, but just in case you do not remember how to assign oxidation numbers, oxygen is a great place to start. It is -2, yeah, in most cases, unless it's peroxide. That would be -2, -2, -2. Hydrogen is +1. So if I add up all my negative charges there, that's 2, 4, 6 on the negative side. -6 plus 1 is -5. The chlorine here is rocking a +5 oxidation state in this particular case to balance it out to 0. We do it for the guy on the right. -2 for this oxygen is oxidation state. -2 is oxidation state. -2. Once again, +1. That means here again, the bromine is also rolling with a +5 oxidation state. As you may remember, if not, we'll review it shortly here, but remember that these things are covalently bonded, which means they are sharing electrons. So these elements do not take on the charges that you may associate with it in an ionic compound where electrons are being transferred, where we normally think of chlorine and bromine as having a -1 charge. In this case, because they're hooked up with the oxygen, the difference in electronegativity makes those electrons shared very unequally, and it actually takes on a more positive charge in the situation when it's sharing electrons, and that's why it gets to a +5. So clearly the central atom here, chlorine and bromine, both have the exact same oxidation state, which means you can't use that to determine the difference between them because they're exactly the same. So in that case, when you have a central atom, essentially the central atom has the same oxidation state of what you're trying to compare, then you should look at electronegativity. Electronegativity, right, is the ability of an atom to bring electrons towards itself, right? And it increases which way on the periodic table? Up and to the right, with fluorine being the most electronegative, right? And decreases as you go down. So when we compare the electronegativity values of Cl and Br, Cl is higher up in that group, which means it's more electronegative. What does that mean? What is that going to do? Well, it's going to do this. We already have our electrons heading in this direction to start with on that OH bond. We now have this guy with the higher electronegativity, which is going to keep bringing those electrons in closer to the central atom. That is going to continue to weaken this bond and allow this guy to come off much easier than it will in this situation, because the bromine is not going to pull the electrons in as close to it as the chlorine will, because it's less electronegative. So this bond, although it is weakened, will not weaken as much as the guy on the left. So because the guy on the left here's bond will really weaken because of that difference in electronegativity, that hydrogen is going to pop off easier than the other guy, making this one our winner here in terms of comparison. That is going to be our stronger acid in this particular case. Any questions on that? By the way, that is chloric acid and bromic acid, right? We're looking at there now. Any questions on that? So oxy acid, if you have the same oxidation number, you want to look at electronegativity. So what is the other situation? The other situation is you have an acid or a couple of acids you're comparing, and actually they're all the same element, or they have the same electronegativity. So obviously here the central atom in each of these cases are chlorine, which means clearly it has the same electronegativity because they're all the same element. So again, we cannot use electronegativity to help us decide. So here we actually do use oxidation numbers. So once again, starting here at top right, oxygen is -2. This oxygen is -2. This hydrogen is +1. That's a -2. -2 is -4. +1 is a -3. That is how we get to the +3 here, as the overall charge is 0, right? So everything needs to add up to 0 in this case. Coming here, -2 +1. That means that we have an overall -1 charge. That is how the chlorine gets to +1 in this situation. This is the one we did a second ago. -2, -2, -2, +1 gets us to our +5 there for our chloric acid. And -2, -2, -2, -2, and a +1. That's a lot of -2s. That's a -8, and +1 is a -7. That means the chlorine here is a +7 in this particular case. In this case, the one with the largest oxidation number in terms of the central atom is perchloric acid. It's going to essentially do the same thing. It's going to take this weakened bond and bring it in because it's way more positive, right? So it's going to bring those electrons in, going to allow this hydrogen to pop off easier than over here, where it's not going to be brought in as much. It's going to hold on a little tighter because it doesn't feel that stronger attraction. Remember, opposite attracts, right? And the strength of the opposite attraction increases with the charge that increases, right? So the higher the positive charge, higher the negative charge, going to be more attracted to each other. So in terms of strong acid to weak acid, perchloric would be our strong, our next strongest, and our weakest out of all of them would be our hypochlorous acid. By the way, in terms of oxidation state of the chlorine, it gets more positive every time we pop on an extra oxygen, yeah? Because that oxygen is going to suck the electrons out of it, making it more electron deficient, and that's why it becomes way more positive at the end there than it does over here, where we just got one oxygen trying to suck the electrons towards itself. Question on that there. Yeah. All right, so let us then talk about salt. Good talk, but let's talk maybe a little bit more about that. I feel like that was a little anticlimactic there. So how do we get a salt? Just a reminder, right? If we take our friend an acid, we dump a base with it, we get water, right? And a salt. A salt is a ionic compound, right? It is really an ionic compound that essentially is derived from an acid and a base. So it's essentially what's left over after you make water, in a sense. So whatever is left over in terms of what you make water is a salt. It is what you probably will remember as spectator ions when you did like double displacement reactions, net ionic equations, and that type of stuff. It's like those spectator ions that are kind of left over. They actually are the salt part in an acid-base reaction. So why is a salt important? A salt is important because it has the ability to continue to react with water. It's obviously sitting in a beaker or whatever water. And if you generate this salt, it actually will continue to react with it and actually affect the pH. The important relationship that we see with salts is this. It is that relationship that we talked before about Bronsted-Lowry sort of relationship. If I have a strong acid, right, are a strong base, the partners to each of those, which is the conjugate base, are the conjugate acid. Are the conjugate base or conjugate acid strong or weak? What is the relationship there? It is, as we talked about, a opposite relationship. It is actually a relatively weak conjugate acid or conjugate base. If I started with a weak acid or a weak base, their partners, the conjugate base and the conjugate acid, are going to be relatively strong. So remember, the sort of opposite relationship. What we're talking about here again is just our Bronsted-Lowry definition, right? Difference between those things, 1H plus, those partners that develop, these guys are going to be relatively strong. So this is the part of the situation where we talk about what relatively strong means. And what relatively strong means is if you have a salt that has come from a weak acid, let's just say this salt came from a weak acid, that would mean that the salt will actually act as a base. Yeah? So it's not a weak acid itself, it actually came from a weak acid. So it will actually act as a base. And that's important because when it reacts with water, which is basically in that solution with it, it's going to act as a base, which means based on the Bronsted-Lowry definition, the acid is going to then be our water, and that is going to donate over an H plus to the salt. The result of that is you will make hydroxide in that solution. Yeah. And if I'm starting to make free hydroxide in that solution, the pH most likely will end up being basic. Yeah. By the way, if I'm doing a calculation, what type of K value should I use in this? Yeah. So these are the problems where they give you the wrong K values. So in this case, when you write the equation correctly, you have hydroxide, you're going to need to use a Kb value. Now let's just say that I had a salt that actually came from a weak base. That means that this salt is actually going to act as an acid in this case. So when it reacts with water, in this case, water is going to actually act as the base. Remember, water is amphoteric, which means it could act as an acid or a base. And in this case, the salt's actually going to send an H plus over to the water. And when it does so, that's going to make H3O plus, yeah? And now I'm making some H3O plus in my solution, which means my solution then will probably be acidic. And if I'm doing a calculation, I probably need a Ka type situation in this situation. So again, this part of it, really important to be able to write the equations correctly and know if you're actually producing H3O plus or OH minus, because again, it will help with the calculation part. Yeah.
Well, to be an acid, it has to have H plus already within it, or just a hydrogen bond.
Yeah, it has to, because if salt's going to act as an acid, it does need to have an H to give. Yeah. And clearly, if it doesn't have an H to give, don't overlook just common sense of it cannot give an H it doesn't have, right? So it's probably going to be a base, right? So you're absolutely right. There are some that could actually go both ways. Just like we talked about those amphoteric stuff. You can have an amphoteric salt that can, in certain cases, act as an acid, and in certain cases, act as a base. You know, something like we saw earlier, you know, something like this, right? It has an H, it can basically donate it. It also can accept it as well. So depending on the situation, it could actually go either way. And we'll talk about how you know which way something like that will go in just a bit. Yeah.
Also the trickiness of the question would be saying, you have a weak acid and it has a Ka of et cetera, but we have to know that its salt dissociates into a base.
Yeah. So the question truthfully in these will just be like you have you know, whatever molarity salt solution, and they'll give you the actual salt. They'll go like, hey, sodium fluoride or something like that. And then what they'll typically give you is like, hey, the Ka value for HF is whatever it is. And they want to just know the pH. So they oftentimes won't just tell you anything in like lights to say, hey, this is a salt or anything like this, you know, this is like hydrolysis happening. They won't do that. So the tricky part of that is people just kind of go on autopilot because they may not understand clearly what's going on sometimes. And they see a Ka and they go, well, okay, I'll just kind of do like the acid move because that seems like a good idea. And it will be completely wrong in this situation because you actually will need a Kb value. So again, understanding what's going on in the problem, like we talked about earlier on in the semester, really, really important in these chapters we're getting into, that you could write the equations correctly and do the math correctly as well. All right, so let's talk about some of these different types of salts that we come across. So first off, there are some neutral salts. And remember the relationship that we talked about a second ago is if the salt comes from a strong acid or a strong base, the salt will be pretty much weak. And what that means is it's basically a neutral salt. So this salt right here, which is sodium chloride, most likely if you had to take a guess at it, what acid did this probably made that salt? Yeah, hydrochloric acid is a very good guess there, right? Because we got some Cl, right? And if you had to guess, the base most likely came from sodium hydroxide, yeah? This is a strong acid, strong base situation, right? It is ultimately a double displacement reaction, right? So this H and this OH is going to make water. There's our spectator ions, right? Cl minus and sodium. They're going to come together to make basically this salt. So sometimes with salts and when you're dealing with these type of situations, it's good to sort of think about where it came from. Yeah. And there's oftentimes a lot of really helpful hints in the problems to help you decide where it came from. But it's good to think about it like one step backwards because, again, it will help you understand what's going on. So in this case, with the sodium chloride, we basically have these two ions floating around, and neither one of them are going to be strong. They're both going to be weak because they did come from basically a strong acid and a strong base. So any salt that comes from a strong acid are from group 1 and 2 on the periodic table, except for beryllium, is going to be a weak sort of salt and will be neutral, which means the pH of the solution should be our pH of 7. In that case, it should be a neutral pH. And that when we talk about group 1 and group 2 from the periodic table, it is really, if you want to think about it this way, that again is where a lot of our strong bases come from. So really it's the same idea as what we talked about, even though they kind of just call it group 1 and group 2, but that's ultimately where a lot of the strong bases come from. And that's why we don't worry about those. So the good news is if you got one of those type of salts rolling there through, it's going to be a neutral solution. The pH should be 7 and everything should be happy. Now, we can have basic salts, and let's just say you got some sodium acetate. That seems like a fun one there. So you have sodium acetate, and when you have a salt solution, what you want to really think about is this. what are basically the two ions that make up this salt? So if this was in solution, it would not stay together because salts are a strong electrolyte. They will 100% break apart into sodium ion and an acetate ion. So basically, if you have that salt in solution, it's not hanging out together. They're basically broken apart and they're floating around. So what we want to think about here is, will any of these ions that are produced from this salt, will they go through what is referred to as a hydrolysis reaction, which is a fancy way of saying it's going to go react with water, basically. Yeah. So will any of these guys continue to react with water? So we already know by what we just talked about, which one can we eliminate for sure? Yeah, the sodium is basically going to come from a strong base or group 1, and it is a neutral salt. So we don't have to worry about really the sodium doing that. By the way, again, if we had to kind of think about what acid and base produce this, probably sodium hydroxide, right? It would be the base. The acid would most likely be, by the way, that's acetate. So the acid most likely would be, there you go. That's acetic acid, right? Little vinegar action here, right? Now, acetic acid, which is pretty much where acetate came from, is that a strong acid or a weak acid? It is a weak acid, and I know that by the process of elimination because I got a 6-pack of strong acids, which is hydrochloric acid, right? Not that. Sulfuric acid, counting with me, I'm going to mess up. Perchloric acid, not that either. Hydrobromic acid, hydriodic acid, I missed one. I don't remember. You want to start again? Sulfuric acid. I think maybe that was the one I missed. Nitric acid, perchloric acid, hydrochloric acid, hydrobromic acid, and hydriodic acid, right? So it's not one of those 6 there. So clearly a very good guess would be it is a weak acid. And that's important because for 2 things, right? I know that it has now come, that acetate comes from acetic acid, which is a weak acid, which means first off, would I expect that acetate to react with water and go through hydrolysis now? Is it going to be weak or strong? If it comes from that weak acid, is it going to be weak or strong? Strong, opposite relationship, right? So I know that this guy is going to be relatively strong. Again, not like a strong acid or base, but it is strong to react with water, basically, right? The other thing that this will also tell me is, based on the Bronsted-Lowry relationship, if it came from this guy, which is an acid, what type of thing is that guy? Is it an acid or a base? So when we did Bronsted-Lowry, right, there was an acid on the left, right? Partner on the other end was a conjugate base. Base on the left, his partner is a conjugate acid. So in this case, this would be like your guy on the left, right? Acid. That means the acetate is going to be the conjugate base. And that's really important to help you understand that this guy is going to basically act as the conjugate base. And now you pretty much have everything that you need to know to write the equation correctly. And let's see how we can figure that out. Well, we're going to take the acetate, which we have already determined that it is going to act as a base. And in these salt reactions, they are hydrolysis reactions, which means it is always water there with it. Which means if my acetate's acting as a base in this case, my water is going to act as a acid. And the definition of a Bronsted-Lowry base is, will it donate the H plus or accept it? That is the answer there. So it's going to, in this case, accept the H plus from the water, right? And when it does that, it will always, 100% of the time, make where it came from, right? And it came from that. It's going to make that guy right there. So the salt, when it reacts with water, will always make where it came from. Now you may be asking, why am I emphasizing that? I am emphasizing that because in a problem, a true problem that you have, they probably would have given you the Ka value for acetic acid, probably written in the problem, which means that is what you get on the product side. Yeah. So there's a lot of information that will actually be in the problem that sometimes people overlook. And you want to understand that. The other important thing is it will make acetic acid, but when this water gives away its H plus, what is it left with? OH minus. Yeah. So in this case, I will produce hydroxide. So even before I pick up my calculator to do the calculation, I should already know that my pH should be acidic, basic, or neutral. It should be basic in this case, right? Because we're producing hydroxide. So again, these are the things you want to think about as you're doing these problems. You should definitely hit basic. The double jeopardy question is when I go to do this ice table calculation, by the way, since it is an equilibrium, what type of K should I be using here? Yeah, you should be using the KB, but you were probably given the Ka value. That also is not a problem for us because we saw a slide 6 slides back, maybe 7, that the Kw equals Ka times Kb when we tie it all together there. That is where we're going to use this probably a lot of the time because you will take the Ka value, you will use that expression, and you will now have the proper Kb value, hopefully, when you go into your ice table. By the way, the last thing here is when I do solve for X in my ice table calculation, X will equal the hydroxide concentration, right? Which means I probably need to calculate the POH first and then go over to the pH. Question on that? I need a drink of water for the recording. All right, so basic salts are produced from basically a salt that came from a weak acid. So again, if you could determine that that salt or part of the salt came from a weak acid, it will then continue to react with water through a hydrolysis reaction. And it will always produce hydroxide in this case because it's always going to act as a base. It will always accept the H plus, and that will always produce OH minus from the water when it does so. Any questions on basic salts there? Yeah. Yeah, so this is what we were talking about a little bit ago. How do you know which one you should be using? And again, it comes back to, I don't know how many times I've said it, but it does come back to being able to write these equations correctly. Because if you wrote this equation incorrectly, which very often happens on a problem like this, people will just take like acetic acid and break it apart into H plus and acetate. Now you're looking at an equation where you see H plus and you're thinking acid, and you're going to use that Ka value and you go, I'm probably right because look, they gave me a Ka value, right? So I'm probably right. And you're going to do it and you're going to get the wrong answer because of that. So again, it's really important to be able to write those equations. And to answer your question, I know I need to use that Kb value because of what is being produced here. The hydroxide is being produced. Yeah. Other questions? All right. We did neutral and basic, which means there's got to be acid salts left as well. So we can have an acid salt. We'll do ammonium chloride. That sounds like a good one. So if we have a salt like ammonium chloride, right? Again, if we look at ammonium chloride in solution, it will break apart into NH4 plus and Cl minus. And again, all salts are pretty much strong electrolytes, so they will not stay together when they go for a swim. They will pretty much 100% break apart into these ions. So once again, we want to kind of do our determination here of, do we have any ions from this salt that's going to go through hydrolysis, that's going to react with water? We'll start with our chloride. Will our chloride do anything? Chloride most likely came from what acid? I agree with you. So that's hydrochloric acid. Hydrochloric acid is a strong acid. I'm not going to count it again, but that's one of those 6 strong acids there. which means the Cl should be a neutral salt, right? And weak. So we do not need to worry about the chloride in this case. How about the NH4 plus? Where did it most likely come from? What base sort of looks like that? Yeah, ammonia, right? And that is a strong or weak base. That is a weak base, right? And because ammonia is a weak base, and that's most likely where that NH4 plus came from, will the NH4 plus go through hydrolysis here and react with water? Yes, I think I heard somebody say yes. So yes, and that is because it comes from a weak base, which means it's going to be relatively strong. We want to think about it like we did before. If it comes from that weak base, when it reacts with water, will it react as an acid or a base? It will react as an acid because it comes from a weak base, which means technically speaking, that's like your conjugate acid, right? And now that I've identified that, I know how it's going to react because all I have to think about is the Bronsted-Lowry definition. Bronsted-Lowry definition of an acid, it will do what with the H plus? Yeah, we'll donate it, right? So now we could actually write our equation hopefully correctly. Because this is a hydrolysis reaction, I perhaps should have water in it on the left-hand side. And in this particular case, it's going to act as an acid, which means actually the NH4 plus here is going to send the H plus over to the water. Water in this case is actually acting as the base in this case, right? And when it does so, NH4 plus the salt will always produce where it came from, right? So if I take off at H plus, I am back to, as you correctly said earlier, where it came from. Once again, in this type of problem, you probably will be given the Kb value here of NH3 is 5.6 times 10 to the minus 8. And again, you will probably have that information, but that again is where we're going to produce. The water then will become what? When it accepts the H plus. H3O plus, that's the hydronium ion, right? That right there should tell me this solution should be acidic, yeah? Because we're producing H plus, H3O plus. Also, when I do my favorite thing ever, which is an ice table in this class, what type of K value will it be? It will be a Ka value that I need. Once again, you're most likely going to have to use the Kw equals Ka, Kb to do a little flip around there. In this case, though, when I do my ice table and I actually solve for X, what does X equal? It will equal the H plus concentration, which means you could go directly into the pH equation to get the pH in this case. So if you have a salt that basically started out as a weak base or from a weak base, it will be relatively strong and go through hydrolysis. It will always act in this case as an acid and donate the H plus to the water. That is how we're generating the H3O plus that affects the pH, right? And that's going to make it more acidic in this case. Question on that there. There is another way that sometimes we can get an acidic salt, and it involves metals that have a high positive charge. A lot of times it involves transition metals that have a high positive charge. I'm just going to go with my friend aluminum, maybe. There it is. So if we have aluminum with 6 waters around it, that is essentially aluminum in the aqueous solution. So basically what it looks like, if I can badly draw it, is we have aluminum and it is attached to 6 waters. Is basically what the 6 means there. So there are 6 waters. I'm just going to draw 5 of them like this. By the way, the water should actually be attaching through the hydrogen or the oxygen in this case. It is the oxygen because in water, right, the oxygen is more negative. And that aluminum is positive, right? So opposite attraction there. So that is how they're attached. The 6 water there, I'll just draw out like that. And in this particular case, what's going to happen, by the way, all the waters are neutral, right? And the +3 charge here comes from the aluminum that has a +3 charge, right? So that's where that +3 charge comes from. Another water that just so happens by itself was out for a swim. It's going to swim by here. And basically what that water, not attached to anything, just going to swim by, is going to help himself over there to one of those hydrogens. And the result of that is this guy will now gain a hydrogen and become our friend H3O plus in this case, right? And that is going to make the solution acidic because now we're generating some H3O plus. Now this thing over here scares people when they look at it. They usually go, that thing, whatever that thing is there. By the way, then in a later chapter, you'll actually name that thing correctly in a later chapter, believe it or not. It's something to look forward to. Maybe, I don't know. But let's just see how we get to this formula, right? We started with 6 intact waters. We actually only used up 1 here, right? Which means we still had 1, 2, 3, 4, 5 intact waters still available, right? We took off a hydrogen from one of the 6 waters, which when we take the hydrogen off, leaves us a OH. So that's where that comes from. And by the way, OH is really OH minus. So +3 and -1 gives you a +2 left over in case you're curious where all those parts come from. So how we produce a acidic salt in this situation is a metal, usually, like I said, a transition metal is usually the ones that will do that. Copper, for example, is another one that can do it. +2, +3 type charges have the ability to do this because in solution, when you write aqueous next to something, that's the deal. They're basically surrounded by water. Yeah, so that's basically what the aqueous means. So they have those waters there. And as we'll talk about in a later chapter, water is a really good Lewis base, which means it can donate a pair of electrons in a situation like this. So it will always pull off one of those hydrogens from the water that's attached to the metal. It will end up producing basically H3O plus in solution and will create it being an acidic solution in that case. Any questions on that there? That is something to digest for a bit. Let's do that.